have to confess something. A couple of months ago, I had this brilliant idea for a custom bracket, to hold my headphones under my desk.
Okay.
I sketched it out on a napkin. It looked perfect. I even downloaded some free 3D software to try and, build it.
How'd that go?
I spent maybe 6 hours fighting with the mouse, just dragging shapes around. I finally got something that looked, well, vaguely correct. I 3D printed it, and it was a complete disaster.
Let me guess. The screw holes didn't line up.
Not even close. And when I tried to go back into the file to just move the holes, like 2 millimeters, the entire model just exploded. Faces disappeared, geometry flipped inside out. It was a total mess.
The classic spaghetti cat experience. You fell into the gap.
The gap.
The massive chasm between having a mechanical concept in your brain and actually having the rigorous execution-ready skills to build it in a professional environment. And that right there is exactly what we're unpacking today. We're doing a deep dive into an educational roadmap. It's titled Mastering Solidworks, From Mechanical Foundations to Industry Design.
And honestly, when I first saw this, I was a little skeptical. I mean, there are a million YouTube tutorials out there, right? You type how to extrude a box and you get 50 videos. Why do we need a structured roadmap for this? Isn't it just about learning which buttons to push?
And that is the misconception. That's what leads to the exploding headphone bracket. This source material, which is basically a comprehensive curriculum, argues that knowing the buttons is actually, well, it's the easy part. The hard part, and what this roadmap focuses on, is mechanical design.
Which brings us to our mission for this deep dive. We're going to see if this curriculum can actually deliver on its promise. To take someone from, and I'm quoting, zero to industry ready. And I want to grill you on that phrase, industry ready, because it sounds like a bunch of corporate buzzword soup.
It does sound a bit corporate, doesn't it? But in the engineering world, industry ready has a terrifyingly specific meaning. It means you can produce a file that, when you send it to a $500,000 CNC machine, doesn't cause the machine to crash and, destroy itself.
Okay, stakes are high. Got it. So looking at the target audience here, it lists students, engineers, and professionals. Students, I get. Professionals, sure. But engineers.
That caught your eye.
It did. If you have an engineering degree, shouldn't you already know how to design a part? It feels like selling a how-to-cook course to a professional chef.
You would think so. But here's the reality of the industry that this source is tapping into. Engineering school teaches you physics. It teaches you thermodynamics, statics, material science.
Why?
Exactly. You know why the bridge stands up. But very few engineering programs actually teach you the deep tactical workflows of a tool like Solidworks.
So you have these brilliant people who can calculate the load stress on a beam, but they can't actually model the beam in 3D without making a complete mess of the file.
Precisely. I've worked with senior engineers who become bottlenecks because they're still, designing on paper or using 2D tools.
And they have to hand their sketches off to someone else.
Right, to a drafter, to digitize. This roadmap specifically mentions engineers looking to upgrade your skills. It's targeting that professional who realizes the tool set has just moved on without them.
The upgrade. I like that. It's admitting your education didn't just stop when you got the diploma.
And it's not just about learning a new software version. It's about a fundamental shift. The source draws a hard line between two concepts, 3D modeling and mechanical design.
I use those interchangeably. I assume most people do.
Most people do, and they're wrong. 3D modeling is just geometry. It's digital sculpting.
Like for a video game character.
Exactly. It just needs to look right. Mechanical design, which is the core promise of this roadmap, is about function and intent.
Intent. That's a heavy word.
It is the most important word in CAD. Design intent means you aren't just placing a hole, you are defining that hole's relationship to the edge of the part.
So that if the part gets longer,
the hole moves with it. Or maybe it stays centered. You are building logic, actual logic, into the shape.
So when I tried to fix my headphone bracket and it exploded, that was because I had no design intent.
Precisely. You were just modeling shapes. You weren't designing a parametric system. And that leads us right to the first pillar of this curriculum. The source breaks the learning down into 3 distinct stages. The first one is parametric 3D parts.
Okay, let's dig into this. Parametric. We hear it all the time. It sounds like math.
It is math, but it's visual math.
Yeah.
In a parametric modeler like Solidworks, everything is driven by dimensions and relations. You don't just draw a line. You say, this line is 50 millimeters long, and it is perpendicular to that other line.
Why is that distinction so critical for a beginner, though? Why not just drag the line until it looks good?
Because in the real world, the design always changes.
Always.
Your boss comes in and says, we need this part to be 10 millimeters wider to fit the new battery. If you just dragged lines, you have to rebuild the part from scratch.
Which is what I had to do.
Right. But if you designed it parametrically, you change one number, you type 60 instead of 50, and the entire model updates instantly, keeping all the proportions and holes exactly where they need to be.
That sounds like magic. I'm guessing there's a catch.
The catch is you have to be disciplined. The source emphasizes building a strong foundation here, because if your parametric constraints are wrong, if you reference the wrong edge, when you make that change, the model breaks. We call it the Christmas tree effect because the feature tree just lights up with red errors.
The red errors of doom. I've seen them.
This course aims to prevent that. It's teaching you to think like a chess player. You're thinking 3 moves ahead.
Yeah.
If I dimension this from the left, what happens if the part shrinks? That is the difference between a modeler and a mechanical designer.
Okay, so pillar 1 is mastering the part, the single widget.
Yeah.
You make it robust, you make it intelligent. Then the roadmap moves to pillar 2, assemblies.
And this is where things get real.
To me, an assembly just sounds like putting the parts together. Like, well, I was going to say Legos, but that feels way too simple.
It is too simple. Legos always fit. In the real world, parts don't always fit. The assembly environment in Solidworks is, well, it's a truth teller. It's where you find out if you messed up.
How so?
You might have designed a beautiful piston and a beautiful cylinder, but when you bring them into the assembly environment and mate them together, you might find out there's zero clearance. The piston won't move.
Or they overlap.
Or worse, they overlap. This is called interference.
And the software actually tells you this.
If you know how to ask it, yeah. The roadmap emphasizes assemblies not just as a way to make a cool picture of the final product, but as a validation tool. This is where you check for fit, form, and function.
I see. So you aren't just grouping files in a folder. You are digitally building the machine to see if it works before you spend money cutting metal.
Exactly. And there's a hierarchy here that the source implies. You have bottom-up design, where you make parts and then stick them together. But as you get more industry-ready, you start looking at top-down design.
Top-down.
That's where the assembly actually drives the parts. Imagine designing a car. You don't design the door handle first. You design the shape of the car, and the curve of the door dictates the shape of the handle.
I see.
The source hints at these more advanced workflows by placing assemblies as the bridge between the parts and the final output.
Which brings us to the final output, pillar 3. And this is the one where I feel like I need the most convincing. Professional engineering drawings.
The 2D drawing, the unsexy hero of engineering.
But seriously, it's 2026. We have 3D printers. We have CNC machines that read code directly from the 3D file. Why does this roadmap place such huge emphasis on 2D drawings? Is it just nostalgia?
Not at all. In fact, if you send just a 3D file to a machinist without a drawing, they might refuse the job.
Really?
Or they might charge you double.
But why? The 3D file is perfect geometry. It's infinitely precise.
That is exactly the problem. The 3D file is too perfect. It says a hole is exactly 10.0000 millimeters, but in the physical world, nothing is perfect. You can't manufacture perfection.
You can only get close.
You can only get close. The drawing is where you tell the machinist how close they need to be. That's called tolerance.
So the drawing is the contract.
It is literally a legal document. The drawing says, I need this hole to be 10 millimeters plus or minus 0.1 millimeters. If the machinist delivers 10.05, you have to pay them. If they deliver 10.2, you can send it back. The 3D file doesn't have that information.
So without the drawing, the machinist just has to guess.
Yes. And if they guess wrong, your part doesn't work. Or they assume you need it to be perfect, so they spend 10 hours polishing a part that didn't need polishing, and they bill you for it.
Okay.
The source emphasizes professional drawings because this is the language of manufacturing. Things like GD&T, geometric dimensioning, and tolerancing, that's the grammar of that language.
It seems like the source is making a really specific point here. You aren't a mechanical designer until you can communicate your design to the person who has to actually build it.
Bingo. You can make the coolest parametric 3D part in the world, but if you can't generate a readable, standardized drawing for it, it will never exist outside your computer.
So we have the 3 pillars: parametric parts, that's the intelligent geometry, assemblies, the virtual validation, and drawings, the manufacturing contract. Now, I want to look at how this roadmap proposes to teach this. The text uses the phrase step by step about 5 times.
Which usually sounds boring.
It sounds incredibly boring. It sounds like chapter 1, the mouse. But why is this emphasized so heavily?
Because a program like SolidWorks is a beast. It has thousands of commands. If you just jump in and try to figure it out by clicking buttons, you develop bad habits instantly. You learn workflows that are slow or unstable.
Like my headphone bracket disaster.
Exactly like that. The step-by-step approach is about layering complexity. You don't learn how to do a loft or a sweep, these complex curvature tools, until you understand the basic extrude. The source is arguing for a linear progression to build what it calls a strong foundation.
It also mentions practical workflows. Now, I challenged industry ready earlier, so I'm going to challenge practical workflows too. How is that different from just learning the software?
This is a massive distinction. Functionality is knowing what a specific tool does, like a hammer drives nails. Workflow is knowing how to build the house.
Can you give me a concrete example?
Sure. Let's say you need to make a bracket with 4 holes. You could draw 4 separate circles and cut them all out. That works. But a practical workflow would be to draw 1 hole and then use a linear pattern command to create the other 3.
Why is that better, though? The end result is the same.
It's about efficiency and editability. If you need to change the spacing later with the pattern, you just change one number.
With the 4 circles, you'd have to move all of them individually.
You might have to move all of them, yes. Practical workflows are the secrets that seasoned pros use to work 10 times faster than beginners. The source is promising to teach you those shortcuts and strategies, not just the button locations.
So it's the difference between just getting it done and getting it done professionally.
Right. And that ties back to that real industry projects claim. It implies the exercises aren't just abstract shapes. You aren't modeling a sphere. You're modeling a distinct mechanical component that requires a specific workflow to manufacture.
I want to circle back to the confidence factor. The source claims it helps you confidently start your career. We've talked about imposter syndrome. Do you think a course like this can actually fix that?
Confidence comes from predictability. When you're a beginner or even a self-taught pro, you have this underlying fear that the software is going to do something you didn't expect. You press a button and you hold your breath.
Oh, I know that feeling. The please don't crash prayer.
Right. True confidence means you know exactly what is going to happen before you click the mouse. You know your part is robust because you built it parametrically. You know your assembly fits because you checked for interference.
And you know your drawing is clear.
Because you used standard tolerancing. That is what industry readiness feels like. It's the absence of panic.
That's a really powerful definition. It's not about knowing everything. It's about trusting your process.
And that is why that upgrade angle for engineers is so crucial. If you are an engineer using, say, 2015 workflows in 2026, you are working harder than you need to. You are likely frustrated. This roadmap offers a path to stop fighting the tool and start actually using it.
It levels the playing field. Whether you're the student just starting out or the 20-year veteran, the software doesn't care. It demands the same logic.
The software is the great equalizer. It rewards structure and it punishes chaos. This source is essentially a guide to avoiding chaos.
So let's summarize the journey here. We start with that desire to build the creator's dilemma. We use this roadmap to master the parametric part, so our designs are intelligent. We move to assemblies to validate the reality of the design. We generate professional drawings to create a contract with manufacturer. And we do it all using efficient workflows so we aren't spending all night at the office.
That is the arc, and the destination is that industry readiness.
It sounds like a lot of work.
It is. But the alternative is sending a file to the machine shop, paying thousands of dollars, and getting back a piece of metal that doesn't fit.
Or a headphone bracket that falls off the desk.
Exactly. The cost of learning the foundation is high, but the cost of not learning it is much, much higher.
I think that's the takeaway for me. We often look at these mastery courses and think, do I really need to go back to basics? But if your basics are shaky, everything you build on top of them is shaky.
And in mechanical design, shaky is dangerous.
So I have one final thought to leave you with. We've talked about upgrading skills. The world of CAD and manufacturing is moving insanely fast. We have AI coming into design, generative design, 3D printing, changing how we structure parts.
It's an exponential curve.
So if this roadmap takes you from zero to industry ready, how long does that readiness last? Is mastering SolidWorks a destination you arrive at, or is it just a temporary status before the next upgrade?
That is the uncomfortable question, isn't it? I think in this field, if you aren't upgrading, you're degrading.
A sobering thought to end on. If you're still drawing lines on a napkin, maybe it's time to look at the roadmap. Thanks for listening to The Deep Dive.
Keep designing. Welcome back to the Deep Dive. Today, we are opening up a file on a problem that I think haunts pretty much everyone in a technical field. It's that really specific cold sweat moment. You've got the degree, you know the theory inside and out. Then you sit down at your workstation, you open the software, and it's just a blank screen. You have no idea how to start.
The blank viewport syndrome, it's very
Yes,
real.
Exactly. It's this paralyzing gap between I know the physics and I know which button to click. And today, we're looking at a source that claims to have, well, built a bridge across that exact gap, specifically for mechanical engineers.
Right.
We're diving into an ecosystem called SGCAD Tech EDU.
It's a really interesting case study
Yeah.
because it's tackling such a modern problem in, engineering education. We've got a stack of their promotional materials here. And what struck me right away is that they aren't just selling information. They're not just saying, here's another tutorial. They're selling a whole methodology for building what they call a strong career.
I want to bookmark that phrase, strong career. That sounds so different from just promising a job or a salary, a strong career. It sounds more resilient.
It implies longevity.
Mm-hmm.
And that's key because the source material is very explicit about who it's for. It targets two groups, mechanical engineering students and, quote, working professionals.
I noticed that, and it felt a little strange to me. Usually these things are siloed, right? You have the intro to CAD for students and then the advanced surfacing for the pros. Why lump them together?
Because in the world of CAD, computer-aided design, the ground is always shifting. The software updates, every single year. Manufacturing standards evolve.
So your knowledge gets outdated.
Exactly. A professional who's been working for 10 years but hasn't updated their personal firmware, so to speak. They're basically back at the starting line with the students.
That's a scary thought. The idea that your skills could just expire.
In engineering, they absolutely do.
Yeah.
And the source material uses this one phrase over and over, upgrade your skills.
Upgrade your skills.
Yeah. It frames your skill set not as some trophy you won at graduation, but as like a living operating system that needs constant patches.
Okay, so SGCAD Tech EDU is positioning itself as the place to get those patches. And looking at the material, it seems like a two-pronged approach. There's a YouTube channel and there's a website.
Right.
Let's start with the YouTube side of things.
This is what I'd call the input phase. The source points us to the SGCAD Tech ED YouTube channel for mechanical design and CAD learning videos.
Okay, I have to play devil's advocate here for a second. I'm a book person. I love a good manual. Why is video so essential here? Why can't I just, read a book on how to design a gearbox?
You can try, you will almost certainly fail. Mechanical design it's inherently 4D.
4D, you mean 3 dimensions plus time.
Exactly. A textbook can only ever give you a snapshot. It shows you the beginning and the end. But design is a workflow. It's a sequence of decisions. You need to see the mouse moving. You need to see how the geometry reacts when a constraint is applied. You need to see the mistakes the instructor almost makes and then corrects on the fly.
It's the nuance of the process itself.
Right. It connects to our mirror neurons. When you watch someone perform a task, even a digital one like moving a mouse, your brain maps that action so much faster than if you're just decoding a paragraph of text.
So the visual learning they talk about is kind of like a modern apprenticeship.
It's the standing over the shoulder method, exactly. 50 years ago, you learned by standing behind a senior draftsman, watching them work. You just absorb the rhythm. Today, that's almost gone. YouTube is the new over-the-shoulder.
That makes a lot of sense. But here's the trap, and I know I've fallen into this myself. I can watch 5 hours of tutorials on, say, how to build a rocket engine. And by the end, I feel like a genius. I feel like I could walk into SpaceX and just take over. But then if you handed me the mouse...
Nothing. That's the illusion of competence. It's probably the biggest danger in all of online learning. Passive watching creates this false sense of mastery. You recognize the steps, so you think you can perform them. But recognition isn't the same as recall.
So how do we break that illusion? Because if SGCAD Tech EDU was just another YouTube channel, it would be contributing to that same problem.
And this is where the second part of their ecosystem comes in. And honestly, it's the most interesting part of all the source material. They don't just want you to watch, they want you to move over to their website, sgcadtechedu.com.
And the call to action changes there. It's not just subscribe, it's register.
Visit our website and register. Sounds like a pretty standard marketing line, right? Did the email. But look at what they offer you in exchange for that registration.
The text says, Register on our website to connect with us. And then there's this very specific line, share your drawings or design documents.
Share your drawings.
That stopped me in my tracks. It sounds so simple, but for an engineer or really any creative professional, that is a huge, huge ask.
It's a massive psychological barrier.
Why is that? Is it about fear of theft, of someone stealing your IP?
A little bit, but mostly it's ego. It's the fear of being exposed.
Exposed.
Yeah. A CAD drawing isn't just a picture. It's a record of your logic. It shows exactly how you think. If your drawing's messy, if your constraints are all tangled up, it's like walking around with your shirt on inside out. It shows everyone you don't really know what you're doing.
It's vulnerability. You're saying, here's my work, and it might be terrible.
Precisely. But the source pairs this very scary request with a specific promise. It says, share your drawings and get guidance and support for your mechanical design journey.
Guidance and support. So it's a trade. You give them your vulnerability, and in return, they give you mentorship.
And that transforms the whole platform. It's no longer a library, it becomes a laboratory.
A library versus a laboratory. I like that.
A library is where you go to consume information quietly, by yourself. A laboratory is where you go to experiment and, break things. By asking users to upload their actual work, SGCAD Tech EDU is trying to build a feedback loop.
And that feedback loop is what's completely missing from just watching YouTube.
Totally. On YouTube, the communication's one way. I broadcast, you receive. But on the website, if this works, it becomes a dialogue. You broadcast your attempt, and an expert responds with a correction.
Let's dig into what that correction might look like. The source says design documents, not just pictures. Why is that distinction so important?
Because a picture can lie. I can make a 3D model that looks absolutely perfect on the screen. It's shiny, the lighting is just right. But if I send you the actual file, the document, you might open it up and see the walls are too thin to ever be manufactured. Or that I didn't account for thermal expansion, or that the parts can't actually be assembled.
So the document reveals the engineering reality, not just the pretty picture.
Exactly. And that is where a strong career is built. You don't get paid to make pretty pictures. You get paid to make parts that don't fail in the real world. And the only way to learn that is to have someone look at your file and say, hey, this is going to break.
It's the red pen moment. Like in school, when a teacher would just cover your essay in red ink. It hurt, but it's what made you a better writer.
And in the professional world, that red pen can be surprisingly hard to find.
That's what I was wondering. If I'm a working professional, say I've been in the industry for 5 years, why would I go to a website for a critique? Shouldn't I get that at my job?
You should, ideally. But think about the modern workplace. Everyone is swamped. Your boss is overworked. Your senior engineer is in meetings all day.
Right.
And if you go and ask for a detailed critique, you might be accidentally signaling that you aren't competent. There's a real risk to asking for help in a corporate environment.
That's true. You don't want to be the person asking, hey, how do I do this basic thing again?
Exactly. So what SGCAD Tech EDU is offering is a kind of third place. It's not home, it's not work. It's this neutral ground where you can practice what I call shadow learning.
Shadow learning, I like that. It sounds like a ninja skill.
It kind of is. It's the ability to upskill in private so you can perform better in public. You go to the website, you struggle with the design, you get the community or the experts to help you fix it, and then you go to work the next day and you nail the project.
So you look like a wizard, but you actually just spent all night in the dojo.
Precisely.
Yeah.
And for the students they mention, this is even more critical. University projects are so often graded on just the final result. Did it work? They rarely have the time to grade the process.
Did you design it efficiently?
Exactly.
Yeah.
And this platform seems to be focused on that efficiency, on the how, not just the what.
I want to circle back to a phrase you hear a lot in this field, design intent.
Yeah.
How does this kind of feedback loop help with something like that?
Okay, so design intent is basically asking this question. How will this model behave when I try to change it later?
Give me an example.
Let's say you're designing a simple box with a hole right in the center. Your intent is for that hole to always be in the center, no matter how big or small the box gets.
Right. Makes sense.
A novice might just draw the hole, say, 5 inches from the edge, because the box is currently 10 inches wide. It looks perfect.
5 is half of 10. Simple math.
But then your boss calls and says, great, now make the box 20 inches wide. Well, if you just hard-coded that 5 inches, your hole is now stuck way over in the corner. It didn't update. Your design intent failed.
Ah, I see. So the expert on the website would have told you to use a formula instead, like box width divided by 2.
Exactly. And you can't really learn that from a generic video because you don't know that you specifically are making that kind of logical mistake until someone points it out in your file. That's the real value of share your drawings. It catches the logical errors that passive tutorials always miss.
That's a really clear distinction. It's the difference between knowing the vocabulary and knowing the grammar.
That's a perfect analogy.
Mhm.
The YouTube channel teaches you the vocabulary. This is an extrude, this is a fillet. The website and its feedback loop teach you the grammar, how to structure those things into a coherent, robust sentence that a machine can understand.
The source material also uses the word community. It says, join our learning community. Do you think that implies peer-to-peer help too? Or is it just a teacher-student thing?
The phrase connect with us suggests a core team. But these platforms almost always evolve into peer networks. And that's actually where the working professionals get a ton of value.
How so?
Well, the best way to really learn something is to try and teach it. If I'm a professional and I see a student's drawing on the forum, and I take 5 minutes to explain why their tolerance is wrong, I've just reinforced my own knowledge. I just made my own expertise stronger.
So it becomes a symbiotic ecosystem. The students get answers, and the pros get to reinforce what they know.
And everyone gets the upgrade.
Let's talk about that upgrade again. The source says, if you are ready to upgrade your skills, it puts the ball back in the listener's court. It's conditional. If.
It's a challenge. It acknowledges that this isn't passive. You can't just absorb this. You have to be ready. And that implies effort. It implies you're going to have to do uncomfortable things like register and share your bad drawings.
It's a barrier to entry, but maybe a good one. It filters for people who are actually serious.
It filters for people who are serious about building that strong career. If you aren't willing to create an account and upload a file, you probably aren't willing to do the hard work of real engineering design anyway.
So if we were to summarize the whole workflow that SG CAD Tech EDU is proposing here, it really does seem like a cycle.
It is. Step 1 is visual. Go to YouTube, watch the workflow, absorb it.
Step 2 is commitment. Go to the website, register, you stop being a lurker and become a member.
Step 3 is action. Do the work, create the design, and then the scary part, share it, upload it.
Step 4 is feedback. Get the guidance. Let someone correct your thinking, your design intent.
And then step 5 is just repeat. Do it again.
Oh.
And that cycle watch, do, critique, repeat, that's the universal algorithm for getting good at anything.
It's funny, we're talking about mechanical engineering, but this applies to, well, to everything, doesn't it?
Absolutely.
I mean, if I wanted to learn to write or code an app or even cook a souffle, I can watch the video, but until I actually make the souffle and have a chef taste it and tell me it's undercooked, I'm not a chef.
You're just a fan of cooking, and that is the core distinction this source material is drawing. Do you want to be a fan of engineering? Or do you want to be an engineer?
Do you want to be a fan or a player? That hits hard.
It should, because the information is basically free now. The YouTube channel is free. The barrier isn't money anymore. The barrier is your willingness to be critiqued.
That's a profound shift. We used to think the digital divide was about who had access to information. But now that everyone has the info, the new divide is about who has access to feedback.
Feedback is the new scarce resource. Information is abundant. But wisdom, which is just corrected information, is rare. SG CAD Tech EDU is trying to manufacture that wisdom by building a community.
So for the listeners who are actually in this field, the engineers, designers, the students sweating over a final project, the path here is pretty clear.
It is. The YouTube channel is SG CAD Tech EDU. The website is sgcadtechedu.com. If you feel like you're stuck or you're just staring at that blank screen, those are the tools.
And for the rest of us, the non-engineers, I think the takeaway is to look at our own lives. Where are we just watching?
And where can we start sharing? Where can we find our own version of this kind of community? Because isolation is the enemy of growth. You cannot upgrade your skills in a vacuum.
You need the friction, the pushback.
You need the connection.
You know, it makes me think about the future of work in general. We worry so much about AI and automation taking jobs.
Yeah.
But maybe the jobs that are safe are the ones that require this kind of complex, iterative, human feedback loop. A robot can download the manual. But can a robot understand why the manual feels wrong in a specific context?
Not yet. That design intent, the why behind the what, is still a deeply human thing. And refining that human judgment requires other humans.
So building a strong career is really about building a strong network of critique.
That's the headline right there.
I want to leave our listeners with one last thought to mull over today. We've talked about a lot of technical stuff, CAD, websites, but underneath all of it, we're really talking about a mindset shift.
A shift from protecting your ego to building your competence.
Exactly. So here's the question for you. In your own career, whatever it might be, are you looking for answers or are you looking for critique? Because answers just get you to the end of the day, critique gets you to the next level.
That is the difference between having a job and building a career.
Think about that. Are you hiding your work or are you putting it out there to be torn apart and rebuilt better? Thanks for diving deep with us today. Check out the links, upgrade your firmware, and we'll see you next time.